Today we are breaking down the paper Advancing Open Source World Models by the Robian team, which introduces LingBot-World. Here's the 1-minute version. So this system, LingBot-World, it's an open source world simulator. It's trying to bridge that gap between just, generating video and actually simulating a physical world.
That's right. So instead of just dreaming up the next pixel, it understands things like causality, object permanence.
And the specs are pretty impressive. We're talking minute level generation horizons, so it has actual long-term memory and it can handle high dynamic complexity.
And crucially, it's interactive in real time. Latency is under a second at 16 frames per second.
How does it do it? Well, it's a mix of a hierarchical data engine, so real, game, and synthetic data, and a 3-stage training pipeline.
And that pipeline uses a mixture of experts or MOE architecture, and then a distillation process that turns a slow diffusion model into a really efficient autoregressive system.
And the big takeaway, it's all open source. Code, weights, everything. It's a direct challenge to proprietary models like Genie 3.
It really is the first time we're seeing a truly playable open source world model that doesn't demand, a supercomputer to run.
Okay, so let's get into the weeds. We cover a lot of video generation papers here, Sora, Gen 3, all the big names. But these authors, they throw a bit of shade right in the abstract. They call those other models dreamers.
And it's a fair distinction, I think.
Why? What's the functional difference between a dreamer and a simulator like LingBot-World?
It really comes down to the model's internal logic. A dreamer, which is what most text-to-video models are right now, is basically predicting pixel transitions based on statistical correlations.
Okay.
It sees frame A, and it just guesses what frame B should look like based on, millions of videos it's seen. It knows sky is usually above ground. It knows a car tends to move forward.
But it doesn't actually know physics.
Correct. It has no grounded understanding of causality. It's just hallucinating a plausible continuation. And that's why you see those weird artifacts in those videos sometimes. A car might morph into a bus, or a person walks right through a wall.
Right, because to the model, it's just pixels changing color. It doesn't get that a wall is a solid object.
Exactly. It lacks object permanence, collision rules, all of that. A simulator or world model, the goal there is to synthesize a persistent environment.
So if you crash a car,
the metal crumples. And this is the crucial part. If you back up and look at it again, it's still crumpled. The world reacts logically to what you do.
and that interaction part is the headline feature here. I mean, if you look at figure 1 in the paper, they literally overlay WASD keys on the video. This isn't just make me a video of a drive. This is let me drive.
Yes, it effectively turns the generative model into a game engine. You're not just a spectator. You are actively navigating. And they show examples of driving through photorealistic landscapes, scientific visualizations, even cartoon worlds.
But to get a neural net to behave like a game engine, to stop dreaming and start, simulating, you can't just train it on passive video, can you? We always say data is king, but here it really seems like the type of data is the real bottleneck.
That is the classic garbage in, garbage out problem for world models. If you just scrape the web for video, all you get is passive observation. You see a car turning, but the model has no idea why it turned.
The causal link is missing.
Exactly. Did the driver turn the wheel? Did the road just curve? Was there something in the road? Passive video lacks those action labels. So the Robian team built what they call a hybrid data engine to solve this.
Okay.
They realized they needed 3 specific types of, let's call it fuel, to make this engine run.
Let's break those down. So pillar 1 is real-world footage.
That's the baseline. They use egocentric views, third-person views of people, animals. This is purely for visual diversity and texture fidelity. It teaches the model what grass looks like, how lighting should work, but it doesn't teach the physics of interaction.
For that, they go to pillar 2, game data.
Which is brilliant. Games are basically structured data factories. In a game engine, you have a perfect log of every single event. Frame 1, player presses WW or frame 2. The character moves forward by X units.
So it creates a perfect pair, action and reaction.
Exactly. They harvested a massive amount of this to teach the model what they call action contingent dynamics. It learns that W means move forward and A means turn left. It bridges that gap between your intent and the video output.
Okay, so real video gives it the look, game data gives it the control. But they have a third pillar that I found really interesting. Synthetic data using Unreal Engine. Why do they need that if they already have game data?
This is where it gets a little technical. It's all about the camera. In real-world video, and even in some game footage, the camera's movement is noisy. You don't know the exact focal length or the precise velocity of the camera,
It's an estimation game.
and that estimation introduces noise. If you want a model to truly understand 3D geometry, it needs to know the difference between the object moved and the camera moved.
The classic ego motion versus object motion problem.
Right. If I turn my head left, the room hasn't moved to the right. But to a naive model, all the pixels just shifted. By using Unreal Engine, they can program these collision-free, randomized camera trajectories where they know the absolute ground truth of the camera's movement, down to the millimeter.
So they have a mathematical baseline for how the world should look when the observer moves.
Precisely. It anchors the model's entire geometric understanding.
Now, sticking with the data for a second, because I think this is where a lot of these models fall down, I want to talk about captioning. The paper mentions hierarchical captioning. Usually I just think of a caption as a dog on a beach. Why do they need a whole hierarchy?
Because a single caption is just too messy for a world model. If you tell a model a man runs through a dense forest, and you use that to train the physics, the model gets confused. It has to figure out which part of that is the man, which part is the running, and which part is the forest.
It conflates the actor, the action, and the environment.
You got it. So Robian developed a 3-layer captioning system to disentangle all these concepts. First, they have the narrative caption that just describes the global story, a high-speed chase.
The vibe.
The vibe, yeah. Then, strictly separate, is the scene static caption. This only describes the environment details that shouldn't change when you press a button. Dense pine trees, wet mud, overcast sky.
So the set design.
Exactly. And finally, the dense temporal caption. This is like the blocking in a play. At second 1.2, camera pans left. At second 1.5, character accelerates.
Wow. So they're explicitly telling the model, this change in pixels is because the camera panned. This change is because the character ran. And this background, this stays the same.
It forces the model to learn that pressing W influences the temporal layer, the movement, but does not change the static layer, like, the species of the tree.
That seems incredibly important for consistency. You don't want the trees to turn into skyscrapers just because you started running.
Which is exactly what happens in those dreamer models we talked about. They lack that kind of disentanglement.
Okay, so they have this pristine 3-layer data. Now let's talk about the brain, the architecture. They call it a 3-stage evolutionary pipeline.
It's a good name for it because they aren't just training it in one go.
Yeah.
They're evolving its capabilities step by step.
Stage I is pre-training. We can probably breeze through this. It's the foundation, right?
Yes. Stage I is about building a robust video prior. They're basically acting like a standard video generator here. The goal is just high-fidelity texture generation. Before you can simulate physics, you have to be able to draw the world convincingly.
It's art school for the AI.
Essentially, yes.
Then comes stage 2, middle training. This feels like the real meat of the paper. This is where they introduce the mixture of experts, or MOE architecture. For the engineers listening who might not work with MOEs every day, why switch architectures here?
So imagine you want your model to know everything. Fluid dynamics, vehicle physics, human biomechanics. If you try to stuff all of that into one dense neural network, the computational cost for every single forward pass becomes enormous. Every time it generates a pixel, it has to activate the entire brain.
It's so inefficient, like calling a full medical board meeting just to put on a Band-Aid.
That's a great analogy. MOE changes the game. Instead of one giant dense network, you have a mixture of experts. Think of it like a hospital with different specialists. You have a fluid dynamics expert, a rigid body expert, a lighting expert.
And a router mechanism to direct traffic.
Right. A router decides which experts are actually needed for a specific token or a patch of the image. So for a patch of sky, maybe you only activate the lighting expert. For a car crash, you activate the physics expert.
So you can have a model with a massive total parameter count, huge amounts of knowledge, but the active parameters for any given inference are relatively low.
Correct. And this allows them to scale up the model's capacity to understand complex world dynamics without making the inference time just explode. This is where they bake in that long-term memory and action controllability.
And this stage produces what they call LingBot-World base.
Yes. The base model is the smart one. It has high fidelity, it understands the physics, and has that minute long memory horizon we mentioned. It solves that catastrophic forgetting issue where the world just dissolves into noise after a few seconds.
That's the catch.
There's always a catch.
The base model is slow.
It's agonizingly slow for a real-time application. It uses bidirectional diffusion.
Let's unpack that. Bidirectional diffusion.
Think of it like a sculptor working on a block of clay. They work on the nose, then the ear, then they go back to the nose, refining the whole image simultaneously from noise to clarity. It produces beautiful results, but it takes many, many steps. You can't play a game if each frame takes 3 seconds to generate.
You'd be playing a slideshow.
A very, very slow slideshow.
So this leads to stage 3, post-training, the need for speed update. They use a process called distillation.
Specifically, they switch from that bidirectional sculpting approach to an autoregressive approach.
Autoregressive. That's how LLMs work, right? Predicting the next word based on the last one.
Exactly. Autoregressive generation is more like knitting a scarf. You do row 1, then row 2, then row 3. You're predicting the next slice based only on the previous one. You don't go back and refine the start of the scarf. You just keep moving forward.
That sounds much, much faster.
It is exponentially faster. But usually, switching from diffusion to autoregressive causes a big quality drop. You lose that global coherence the sculptor had.
So how did they solve that?
They use a clever distillation technique. Essentially, they set up a teacher-student relationship. The big, slow, smart base model, the teacher, generates thousands of high-quality trajectories. The lighter, faster, autoregressive model, the student, then trains to just mimic those outputs.
So the student isn't trying to learn physics from scratch, it's just trying to learn how to imitate the teacher who already knows physics.
Exactly. It learns the shortcuts. It learns to approximate the teacher's reasoning, but at a speed of 16 frames per second.
And this gives us LingBot-World fast.
The playable model.
They do mention a trade-off here. The paper says the drop in quality is perceptually marginal. Is that just marketing speak, or is it for real?
It's a bit of both, but I'd say mostly real. The fast model might lose some high-frequency detail. Maybe the grass texture isn't quite as crisp as the base model. But crucially, it preserves the structural integrity. The car still crashes correctly, the building doesn't warp, the logic is preserved, even if the pixels are slightly less refined.
And getting 16 FPS on a single GPU node at 480p resolution, that's the breakthrough. We're not talking about some massive H100 cluster here.
It crosses the threshold from batch processing to interactive. You can actually hook a keyboard up to this thing and drive.
Let's talk results. How do we even measure if a simulator is actually simulating? They use a metric called dynamic degree. LingBot scored a 0.8857. The competitors, Yoom 1.5 and HY-World, are way down in the 0.7s. What is dynamic degree actually measuring?
It's basically measuring the richness of the motion. A low dynamic degree usually means the video is mostly static, or maybe it's just a simple camera pan over a still image.
The Ken Burns effect.
Right. Safe, but boring. A high score means things are morphing, moving, deforming, colliding. It implies that LingBot-World isn't just treating the world as a static painting, it's generating complex, non-linear motions in response to your controls.
And then there's the ultra-long video generation. Figure 13 in the paper shows a sequence that goes up to 10 minutes.
That is the simulator claim being put to the test. 10 minutes is an eternity in generative video. Usually, standard diffusion models suffer from catastrophic forgetting. After 10 seconds, the car turns into a boat, or the road turns into a river.
Or you turn around and the house that was behind you is just gone.
That's the unobserved states problem. And this is where LingBot really shines. They tested for this specifically. If you're in a generated room, you turn the camera 180 degrees to look behind you, and then you turn back.
Does the game look the same?
In LingBot-World, yes. It remembers the geometry. It demonstrates object permanence for things that aren't currently on the screen. And that implies the model has developed a form of spatial memory. It's not just painting pixels, it's maintaining a state.
That is wild. It's inferring a 3D reality that persists even when it's not being rendered. Which brings us to the applications, because if you have that kind of consistency, you can do a lot more than just make movies.
The paper highlights 3 main applications. First is promptable world events. Because the model understands both language and physics, you can steer the world semantically.
So I can be driving the car with W, A, S, and D, but then I can type, the weather turns stormy.
Exactly. Or a dragon lands on the road. You are effectively the dungeon master and the player at the same time. The simulation adapts the physics and the visuals to your prompt while maintaining that interactive loop.
That's incredibly cool for gaming. But what about for research?
That's application number 2, action agent training. This is huge for robotics. If you want to train a robot to navigate a messy house, You can't run it in the real world at first. It'll break things, or it takes way too long to reset the scene every time.
Encoding a traditional simulator with perfect physics for every possible messy room is basically impossible.
Right. But here, you can just prompt LingBot, generate a messy living room with obstacles, and then you let the robot's AI brain practice navigating inside this simulation. Since the physics are consistent and that action-reaction loop works, the robot actually learns.
It's an infinite generative gymnasium for AI agents.
Exactly. And because it handles unobserved states correctly, the robot can learn things like mapping and exploration, not just simple reaction.
The third application they mentioned was 3D reconstruction. I thought this was a really smart validation technique.
It was sort of the mic drop for the skeptics. They took the video that was generated by LingBot and fed it into a Gaussian splatting algorithm.
Okay, quick ELI5 on Gaussian splatting.
It's a technique that takes a set of 2D images-like frames from a video and reconstructs a fully explorable 3D scene from them. But, and this is key, it relies entirely on geometric consistency. If the camera moves left, the perspective of the object must change in a mathematically correct way. If the object warps or shifts randomly, the reconstruction fails. It just looks like a cloud of noise.
So if the video is dreaming and hallucinating, the 3D reconstruction just breaks.
Correct. But LingBot's video was so geometrically sound that the algorithm successfully built a coherent 3D mesh from it. It proves that the 3D consistency isn't just a visual trick. It's mathematically real within the model's latent space.
If the math says it's 3D, it's 3D. So what we have here is a fully open source system code, weights, everything that's challenging the proprietary giants. They're democratizing the ability to build these infinite worlds.
And that really is the why it matters here. The proprietary divide in AI is getting wider and wider. By releasing LingBot-World, the Robian team is giving the entire open source community a testbed. It allows researchers who don't have access to massive compute clusters to experiment with embodied AI to tweak the MOE architecture to improve the data engine.
It just accelerates the whole field. It feels like we are inching closer to the holodeck, a system where you just describe a world and then you step into it.
We are certainly moving beyond passive observation. The authors state their goal pretty explicitly: to ignite a new wave of innovation in infinite, playable, and interactive virtual worlds.
As we wrap this up, I'm left thinking about that 10-minute generation capability and the object permanence. It really does blur the line.
It raises a pretty fascinating question.
If a generative model can maintain consistent 3D geometry and object permanence for 10 minutes, based purely on learning from video, and eventually 10 hours or maybe 10 years, and we're training AI agents inside these worlds.
I see where you're going with this.
At what point does the distinction between a simulation and a recorded reality completely vanish for the AI agent that's training inside it? If the physics are consistent and the consequences are real within the context of that model, is there any functional difference for the intelligence that's growing inside that box?
That is the ultimate conclusion of simulation theory, isn't it? When the simulation becomes indistinguishable from reality, the definition of reality itself becomes, well, flexible.
Something to think about next time you're training a model. That's it for this breakdown of LingBot-World. The code is out there, so if you have the hardware, go build a world. Thanks for listening.